Howdy, my name is Reid Harrison. I am an undergraduate student here at Texas A&M University, and through the TAMU OREU program, I have had the privilege of working with Dr. Zijing Wang and PhD candidate Zui Fan, doing research on 2D perovskite materials. This presentation provides a brief overview of my work. Perovskites are a type of material that can be defined by their stoichiometry and their octahedral structure. My research in particular will focus on lead halide perovskites. Our motivation in studying these perovskites is that they have desirable traits for photovoltaic and optical electrical applications. These applications include LEDs, solar cells, and lasers, just to name a few. Our project's end goal is to successfully create a stable halide perovskite heterostructure. And in order to do this, we must first mitigate factors that affect their structural stability, such as their sensitivity to moisture, and produce more favorable microstructures. The second point is where most of my work applies. In order to grow our perovskites, we use chemical vapor deposition. We can tweak the different growth parameters in order to grow different structures. These parameters include the amount of chemicals used, the pressure, the temperature, the length of time we allow our samples to grow for, and the gas flow rate. And then in order to characterize our samples, we use optical microscopy as well as a spectrometer. And there's two main things we're looking for when we do this. One is to see which shape we produce. Are we producing sheets, nanoplates, nanowires, or some other kind of particle? Are they irregular or regular shapes? And then the spectrometer allows us to see what color they fluoresce under certain excitation wavelengths. Correctly made samples each have a specific color that they fluoresce, and this also verifies the presence of perovskite growth. I will now be providing a brief overview of the work I completed each week. The very first week was primarily about getting used to using the lab equipment and the lab procedures. And here on the right you can see I also grew my very first perovskite sample. This is a cesium lead chloride sample, and we started with this one because we already had an established recipe for the sample. Moving into week 2, now that I had been properly trained on the lab equipment, I was given a new set of chemicals, and we were to try and grow butyl ammonium lead iodide perovskites. This is the very first time we were using this set of chemicals, and so we had to turn to prior literature in order to find a recipe and adapt it to our equipment. We were able to successfully produce irregular nanoplates by the end of the week, which you can see pictured here on the right. And we also learned that these perovskites are sensitive to the light we use to excite them. If we keep the light on too long, they begin to deteriorate. Moving into weeks 3 and 4, we had two primary objectives. The first was to refine the shape of our butyl ammonium lead iodide perovskite, because so far we had only produced irregular nanoplates, and regular shapes or a sheet are more desirable. And then we also were trying to prepare to grow a heterostructure, which in order to do this, we had to find the lowest temperature at which we could still see significant growth. And this is simply because lower temperatures have less risk of causing the existing layer in the heterostructure to deteriorate. And then if we move on to the next slide, you can see that across several trials we produced many different shapes, although they're primarily variations of irregular nanoplates, or we had a few that were sheet-like structures. Additionally, we were able to find the lower limit of growth for our perovskites. This was found to be around 330 degrees Celsius, at which we produced very little growth, as pictured on the right. Now that we've had a few weeks of work done on growing the butyl ammonium lead iodide by itself, moving into week 5, we decided it's time to try and grow a heterostructure. Now what I mean when I say heterostructure is we're actually going to be trying to grow the butyl ammonium lead iodide perovskite on top of cesium lead iodide perovskites, which you can see pictured here in this diagram. And then what we found out is that heterostructure growth is indeed possible. The butyl ammonium lead iodide growth doesn't damage the cesium lead iodide beneath it, which is good. And then we also found out that our samples are extremely moisture sensitive. We learned that we had to collect data very quickly to prevent the cesium lead iodide perovskites from deteriorating when they were exposed to air. And then we also had a few problems with cation diffusion, destroying some of our perovskite structures as well. So ultimately our data produced was not very clean. And then if you look here on the right, we have two images. The top image is our sample excited under blue light, in which it glows green. The green is primarily the butyl ammonium lead iodide, and then you see little bits of orange peeking through, which is the cesium lead iodide. And then on the bottom image, this is our sample excited under green light, and the red glow is the cesium lead iodide. Unfortunately, as you can see here, much of it has deteriorated before I was able to take this picture. And then moving into week 6, we aimed to produce a good heterostructure sample with a higher quality of data than our last set, as well as suppress the cation diffusion that we'd witnessed. And what we found is that growing our samples at a higher pressure can actually suppress the cation diffusion. And we also produced a cleaner set of fluorescence data than last time, which you can see pictured here on the right. We also observed a structure in the butyl ammonium lead iodide that we believe is a sheet, but we weren't entirely sure. So we took some SEM images of our sample. And what we learned from our SEM image is that what we observed of the butyl ammonium lead iodide was actually a bunch of small, closely packed particles rather than a complete sheet. Since we had proven that we could grow a heterostructure in weeks 7 and 8, we instead set out to further refine the shape of our butyl ammonium lead iodide perovskite. And what we're looking for is larger, more regular shapes. So rectangular nanoplates, straight nanowires, or film or sheet-like structures. And we did produce some nanowires, unfortunately not as straight as we'd like. And we also produced a uniform sheet-like structure, which I say sheet-like because, again, these are just a lot of really, really close packed particles. You can kind of see it here pictured on the right. I will now present the results that we have as of the making of this presentation. And so in conclusion, more work must be done, but we are much nearer to producing both desirable structures and better heterostructures. In the past week, I have successfully made some more sheet-like structures, and we even made another really good heterostructure sample. And more importantly, my work has paved a road for further research. Whoever takes over after me should be able to use my data and continue on. Before I go, I will say a few closing remarks, and that is that it has been a real privilege to work as both a part of Z-Lab with Dr. Wong and Zui Fan, as well as a part of the Texas A&M OREU program. I've gotten to learn a lot about laboratory techniques and specifically about chemical vapor deposition, as well as getting to hone my presentation making and presenting skills. Overall, it's been a very positive experience, and I would like to thank you all for watching. That concludes my presentation.